Hello students and welcome to week 4. During this week we will be talking about food processing. Food processing is very important and we're going to apply it to the products that we have been analyzing. The objectives for today are to distinguish between food processing and food manufacturing, to describe food preservation principles, to explain the different types of food processing, which can be divided into chemical, biological, and physical. So what is processing? Sometimes we think about food processing and food manufacturing as the same thing, but there are some authors that distinguish between food processing and food manufacturing. So food processing is what we will call a first level manufacturing, and it will be turning a raw material into an ingredient that will be used by a second level manufacturer. So for example, agricultural processing is when we transform products for intermediate or final consumption, like for example, turning vanilla beans into vanilla extract. So this will be an example of food processing because we're going to use vanilla beans and then extract the compounds, and then the vanilla extract can be used by consumers, but it can also be used by other manufacturers in, for example, using vanilla extract for further processing as an ingredient. Another example is meat processing, and which includes like livestock and poultry slaughter processing and rendering. So this is also a very, let's say, first level manufacturing, which we will have like meat and it's for final consumption. So when you think about food processing, first level manufacturing is like mainly basic transformation of either agricultural or meat for final consumption or as ingredients for further processing. So what's the difference between food processing and food manufacturing? So food manufacturing is like an additional level. So it implies the application of labor, machinery, energy, which can be explained in terms of like thermal pressure or irradiation, and also scientific knowledge. So taking the vanilla extract example, and then we will mix it with flour, sugar, and eggs to make cookies. So in the first part, the food processing of vanilla into vanilla extract, and now we're taking the vanilla extract as an ingredient for further processing. So both processing and manufacture add value to the products. And sometimes you're going to see that they are used as synonyms and they are used like interchangeable. So this is just an introduction about some differences that we can find. So if we think about complexity, we'll think about manufacturing as being more complex and involving more things than processing, which is more basic. So here we have a breakdown of like the different types of food processing and beverage manufacturing, and we can see the different categories like sugar and confectionery, seafood, animal food, bakeries and tortilla products, fruits and vegetables, grain and oil seeds, beverages, other food, and we can see that the biggest ones are meats with 24%, and then we have dairy, which is around 14%. So this is just a classification of the different sectors involved in like food manufacturing, and we can have like a wide diversity of processes that are involved in each of these categories. We can also see in this breakdown of how many establishments or facilities we can find in the different states of the United States, and we can see California has one of the highest manufacturing food processing or food manufacturing in the whole US, and that's very interesting and important. There's a lot of agriculture, a lot of dairy processing, and fruit and vegetables processing. So there's a wide variety of processing in California, and we can see the high amount of companies that dedicate to food and beverage manufacturing. And we can see like the difference between the different states in the US. So how does food manufacturing impact food? So food preservation prevents or delays spoilage caused by microorganisms, chemical changes, or physical changes. So sometimes people think like, is preservation good, processing good, or not? So if we have, like, say, like in the picture, a pumpkin, and we just don't do anything, well, the pumpkin may last for, I don't know, a few days, a week, but then it will spoil because of the action of different things. It can be most likely microorganisms, also chemical changes, which will affect the composition, or physical changes which will affect the texture, and it's going to start like getting soft. So there's many changes that are going to happen to this pumpkin if we just leave it like that. So food preservation is so important for many reasons, but one of the most important ones is to add value to our food, to make food available during the whole year, for example. Also to make food last longer, and that's why food preservation is so important in today's world. So when we think about food preservation, this is a very broad definition, and we can use thermal or non-thermal processing methods during manufacturing to eliminate, inhibit, or delay spoilage organisms in food. So here it's very important to pay attention to two things. One is we can have thermal, which means processes that will involve temperature, or non-thermal. And we're going to talk about non-thermal processing in the next presentation. And the idea in using this type of processes is to, one, eliminate or inhibit. So when we think about eliminate, this means that we can also use another word that is inactivate. So if we eliminate or inactivate, is that we kill the microorganisms, so they are no longer present. If we talk about inhibit or delay, this means that the microorganisms are still there, but their growth rate, or the speed at which they will multiply, is going to be slowed down. And because of that, we will have more shelf life, or more time. And here we have a word that is called spoilage organisms. So in our previous slides, we talked about pathogens, like Salmonella, or E. coli, or Listeria, or Clostridium botulinum. So these are called pathogenic organisms, and these are organisms that if you, by any chance, ingest them, they will make you sick. So spoilage organisms are organisms that will make our food maybe lose the quality they have, impact sometimes the texture, the flavor, but at the end, they are not going to harm your health. Well, we don't like eating something that is spoiled, of course, but the impact they have in our health is not the same as pathogens. And spoilage organisms are easy to identify because we can see in the products that the quality characteristics are changing in terms of texture, or color, or smell, and so. With pathogens, it's more complicated. Sometimes we cannot identify them. So then we eat the food and we get sick. So the other question is an antimicrobial a preservative? So an antimicrobial can be called a preservative, and its main function is to inhibit the growth of microorganisms without killing them. So it will slow down the growth rate of microorganisms. It will not kill them, but this slowing down the growth rate or the multiplication of microorganisms will help us have a longer shelf life. But not all preservatives are antimicrobials. We can have other types of preservatives, which include antioxidants, stabilizers, or anti-browning agents. And when we talk about antimicrobials, and we have talked about that earlier, we have chemicals that are used as antimicrobials, and we also have natural antimicrobials, which are mainly extracted from different types of spices like cinnamon or cloves. So if we don't do anything to the food, as we talked about the pumpkin example, if we don't use any type of antimicrobials, we're going to see spoilage signs like of odors, of flavors, discoloration, slime, change in texture, softening of, let's say, fruits, vegetables. So as I mentioned before, when we have spoilage microorganisms, we can see what's happening. If we see like mold growing like in strawberries, right? They are white, they are fluffy, we can see them. And then we are like, okay, these strawberries are spoiled, I'm not going to eat them anymore. But when we talk about pathogens, they can grow and we cannot see them. So there are no signs of spoilage. So that's more difficult because we cannot see any signs visually or by any of our senses, but they can cause a lot of harm. So it is important to distinguish between spoilage microorganisms and pathogens. So if we are concerned about microorganisms, and here we're talking a lot about microorganisms, there are other things that can also affect food, like for example enzymes, but let's focus for now on microorganisms. So we can control them by three different preservation methods. One is chemical, which is the addition of chemicals for antimicrobial effects. So examples would be when we have sodas like Coke, and if you read the ingredients, you're going to see some chemicals like sodium or potassium benzoate or sorbates, and these are antimicrobials. So one of the preservation methods that is used is a chemical preservation method. Then we have biological, and this is by the production of acids or acidification. And most of the examples are related with fermentation. And then we have physical preservation methods, and these are very, very important, and they're widely used in the industry. So we have drying and freeze drying. We have cold storage, we have freezing or frozen storage, and we have heat treatment. And then we have another type of methods that are called non-thermal processing, and they are alternative to these physical methods, and they have been studied in like the last 40 years, so they are relatively new compared to the others. And we're going to cover the non-thermal processing in our next presentation. So let's start with chemical antimicrobials. So these are traditional chemicals which can be synthetic or natural additives. Sometimes they are not attractive to consumers because all this wave of like organic, natural, and so but they have been very widely used, and they are still widely used in most of sodas. They use chemical antimicrobials. Some of them are naturally occurring, like acetic acid, which is vinegar, benzoic and sorbic acid in some types of fruits. And the natural occurring ones are considered like organic and consumer friendly. And it's important to note that there's no federal regulation that defines what is a natural preservative, right? So as I talked before, we can extract natural antimicrobials from different spices, like I mentioned cinnamon and clove. We can also extract from like oregano, thyme. So there's they have these antimicrobials are specific compounds, sometimes related with also the aroma that we have, the characteristic aroma of cinnamon or clove or oregano or thyme, etc., etc. And these antimicrobials have and are being studied in like different types of food and against different types of microorganisms. So this is something that is very important. Each antimicrobial can have an effect or a different effect in different microorganisms. So sometimes antimicrobials have an effect over bacteria. And then we have different types of bacteria, like gram-positive and gram-negative, that we talk about, that is related with the structure of the cell wall and the cell membrane. But then we have other antimicrobials that are better for or target in a better way molds or yeasts. So it is important to understand that different antimicrobials will target different types of microorganisms, and the same happens with natural antimicrobials. And then one of the greatest challenges of natural antimicrobials is that because, let's say, they have a flavor or a smell, let's say we have a cinnamon or a clove, a smell or flavor, and say in cinnamon, the compound responsible for the antimicrobial effect is called cinnamaldehyde, and in clove, the compound responsible is called eugenol. But let's say we want to add it, for example, to a savory dish or a savory processed dish. So we have to be very careful because maybe the concentrations that we need are high, but we don't want the flavor of cinnamon or cloves to be in our product. So it is something that is still being studied, but it's very important to consider that we can have natural occurring alternatives that can be used because consumers want more natural and organic. But there's also challenges that, as I mentioned before. We also have chemical disinfectants. So these are not antimicrobials per se, but they are important in the processing day-to-day. Because we have a processing plant, and then we have to do, once we run the process, we have to do cleaning, or sometimes it's called CIP, or cleaning in place, in the equipments, in the transportation belts. So there's many things that go into chemical disinfectants and processing, and that you're going to find more about it when you do your food processing assignment. So a disinfectant is not considered a preservative, but it kills or inhibits microorganisms. So some examples are chlorine and sulfur dioxide. There's other options, and when we were facing COVID, we had like a lot of analysis and innovation in like disinfectants, like the hand sanitizers with 70% alcohol and the effect they have in different types of food. And as you can see here, we have a picture of like dried apricots with sulfur dioxide, and you can see the color, and this is what we expect. If we don't use any sulfur dioxide, we will have very brown and dark apricots. So sulfur dioxide is very widely used, not only as a disinfectant, but also as a preservative or additive in dried fruits for preserving both the microbial integrity and the color in this type of fruits. It is also used in say production, for example, of raisins, and it's a very widely used compound. Okay, so another way to preserve food is by controlling the water activity. So this will help in controlling spoilage. And one of some of the solids that are used for controlling the water activity are salt and sugar, and they are added because they bind to water molecules, and then they decrease the availability of water, and this will decrease the water activity. And as we have mentioned and talked before, this will also reduce the availability of water and thus the growth of microorganisms. So we have some products or as examples or products where the water activity is 0.7, and if we recall, we have a water activity that is lower than 0.85, we have a very low probability of microorganisms growth. And we have the moisture content of some foods, like for example grains, and the moisture content between 4 and 9%. We have milk powder between 7 and 10. We have cocoa powder, the same. Whole egg powder, 10 and 11%. Dried fat-free meat between 10 and 15%. Some rice and legume seeds between 12 and 15. Dehydrated vegetables between 12 and 22. Dried soups and dried fruits, and we have the different ranges: 13, 21, 18 to 25. So by removing, in this case, the moisture content or the water, we are increasing the concentration of solids in relation with the water in the food, and then the increase of solids, we can also add some solids like sugar and salt, and then we are reducing the water activity. So we are controlling it, and then we are reducing the growth of the probability of microorganisms growth. We can also see this effect, for example, in jams, jellies. We are adding sugar and we are decreasing the water activity, and thus these type of products will last longer. Of course, these type of processes like jams and jellies are a combination of water activity reduction with a thermal treatment, which involves temperatures. But since ancient times, they use also salt for preservation of meat or hams, like say hams like prosciutto or some types of Spanish style hams. They use salt for the production of this type of cured or meats or hams. So the salt, there's an outer layer of salt, and then the salt diffuses inside the meat, and this helps with reducing water activity and thus preventing the growth of microorganisms. So now let's talk about biological based preservations. And as we talked before, we can add acids like acetic acid, lactic acid, or citric acid. But these acids can also be created by the action of fermentation processes. So some of these microorganisms that are responsible are called lactic acid bacteria, or LAB, and they can be produced as a preservation system. And for example, these are produced in yogurt manufacturing, and also some other types of products like kefir, maybe kombucha, and some other type of products. And we also have some compounds that are called LAB bacteriocins, that are small proteins that are produced by lactic acid bacteria, and they can have an antimicrobial effect to inhibit pathogen growth. One of the examples is called lysine, and this is called a bacteriocin that is available and is widely used in cheese making. Another option would be to use other types of bacteria, like acetic acid bacteria. One of the examples would be like Acetobacter, which is very well known for the production of acetic acid, and it's one of the microorganisms that is involved in kombucha processing, for example. And then we go into physical methods. So these are, let's say, the most important and most widely used methods. And we can talk about drying or dehydration, freeze drying, cool storage, freezing or frozen storage, heat treatment. And we can divide heat treatment into pasteurization and commercial sterilization. And it's important to mention that during heat treatment, all the molecules should reach a specific temperature for a specific time. So in all these methods, we have to keep in mind that we have to control many variables, but the most important variables in all these methods are temperature and time. And so let's take a look into more in depth in this type of methods. Okay, so the first one is drying or dehydration. And we have different types of drying and dehydration, like sun drying, tray drying, oven drying, spray drying. So, and we have some examples here, like say beef jerky, we have the apples, we have whey protein powder. So let's take a look into what is drying. So drying is mainly removing water, as I mentioned before in previous presentations. Most fruits and vegetables and also meat, they have a high amount of water. So let's say fruits and vegetables 85 or more, like 85 to 95% water, and meat, let's say around more than 75%. So because of the high amount of water and water availability, they are easy to spoil. So if we remove the water by drying, and then we can control the microorganisms' growth. So let's take a look, for example, beef jerky. So beef jerky is normally thin sliced meat. So we can use different types of meat. We're not going to get into detail. And these meat slices are marinated. And the marinating process is very important. Normally there's a lot of mixing and like in the tumbler, and sometimes they add vacuum because that helps with the impregnation of the marinade inside the meat. And then these meat slices are dried. So when we talk about drying, we have to expose these meat slices to a specific temperature for a specific amount of time. So depending on what we want to achieve, we have to set the temperature. Sometimes the temperatures are not very high because sometimes high temperatures can lead to burning and also loss of vitamins and so. So the knowledge is how to define the temperature and the time that we require. And then the important part is that after we dry them, we have to package them in a very specific package with specific characteristics, because we don't want our dried jerky to again gain moisture. So if we just leave it there, there's moisture in the environment, as we know, and then the beef jerky will acquire more moisture and then it can spoil. So the packaging is also very important. So, and the texture we want for beef jerky is different from the texture we want for apple crisps or chips. And the same thing happens with apples. We have the apples, we slice them. In apple, it's important to control browning. And we can use several additives like citric acid. And then we also dry them. Normally, we use straight drying. We use temperatures around like 60 degrees Celsius for, let's say, 6 to 8 hours or more, depending. But this is like the knowledge of each of the manufacturers. And then we have whey protein powder. And this whey, as I mentioned before, is a byproduct of cheese making. And then the whey liquid goes through several steps of purification or filtration, and then with whatever is left, we dry them in a technology called spray drying, where we spray, as the name says, the liquid. And so imagine like when we take a shower and there's like particles of water, something like that, but the chamber in which we spray the liquid has a high temperature, and then the particles of water are going to turn into solid particles or powder particles, and that's how we make whey powder. So these are just examples of drying or dehydration, which is a preservation method that is very widely used in a lot of foods, and the idea is to remove water, and with water removal, we can, of course, lower the water activity, and by this, we can decrease the probability of microbial growth. Then we have freeze drying, and freeze drying is a combination of two technologies, freezing and drying, and this is it's relatively new technology, and it was designed for space travel. But now it's used for a lot of products that are or have a high value. And the texture that we get with freeze drying is different from the texture that we get from just drying. And the important thing is that the product retains its original structure. So there's not a lot of changes in texture or shape. And the fast dehydration process, so it allows us to remove around 90 to 90% of original moisture content. And then we have our final product. So the basic idea in freeze drying is that we freeze the product, and then we start, like, we have trays, and we start increasing the temperature of the trays which are in contact with the product, and this helps water evaporation. But the water undergoes a process that is called sublimation, so it changes from solid to gas. So it will not go to liquid. So from solid go to gas, and this is because of the pressure and temperature settings that we have in freeze drying process. And we have an example here of crispy strawberries. So a lot of fruits are freeze dried, like berries, strawberries, blueberries, raspberries, and so. And I would recommend you guys to watch the video how freeze drying works, and because all the videos in food processing are going to be included in our exam too. The next one is refrigeration. So here, the important thing is that refrigeration and as well as freezing, in this case, we are going to lower the temperature. So when we lower the temperature, we are slowing down all the reactions that take place in our food, chemical reactions, microbial reactions, etc. So it's important here to consider that for refrigeration to be effective, refrigerators have to be at the right temperature. And here I'm just leaving the link of a FDA fact sheet about how to calibrate thermometers and how to make sure that you have a thermometer in your refrigerator to be sure that that you are at the right temperature. So normally refrigeration temperatures are around 4 degrees Celsius, which is around 40 degrees Fahrenheit. And when we talk about refrigeration, we have to consider that this process will inhibit microorganisms, so it will not inactivate them. So they're still going to be there, but the process is going to be slowed down because of the low temperatures. And refrigeration is very widely used in the food industry as one of the steps. For example, if we have, I don't know, production of something and they have refrigeration chambers, or for like, say, apples storage. So apples, normally they have a season where they are harvested, and normally they are kept in specific refrigeration chambers at a specific temperature and with the specific moisture, relative humidity, and they can last around a year, for example. So the difference between refrigeration and freezing is the temperature. So we talk about refrigeration, we are above the freezing point of water, which is 0 degrees Celsius or 32 Fahrenheit. When we talk about freezing, we are below that, much lower. And freezing is very important also as a food preservation method. If you think about the supermarket, we have products both in the refrigeration section and in the freezing section. So of course, freezing, because we're using lower temperatures, we have a phase change, they are solid, and it also inhibits microorganisms, but they slow down the reactions to a larger extent than refrigeration because we are using lower temperatures. And we think about frozen products, we have a lot of examples in the supermarket, like frozen vegetables, frozen fruits, frozen dinners, etc., frozen pizza, and so. And the shelf life of frozen foods is, of course, longer than refrigeration. And we also can think about refrigerated products like yogurts, like some type of juice, cheese, etc. So the refrigeration and freezing are very important preservation methods, and they require our temperature to be low. So now let's move into heat treatment. So heat treatment, as the word says, heat treatment, we are going to increase the temperature. And these processes are very widely used. And one of the processes is called pasteurization. So I recommend that you watch the videos, what is pasteurized milk and what is lactose-free milk. And one of the most or better examples of pasteurization is milk. So milk in the US is pasteurized, and then it's packaged in plastic containers, and then they are refrigerated. So this preservation method is a combination of two things, both a pasteurization and then a refrigeration. So think about pasteurization as you have milk, and then it is, let's say, at room temperature, then it is heated to a specific temperature, normally 72 degrees Celsius for 15 seconds, or if it goes higher, it will be for 1 or 2 seconds, and then it's cooled down and packaged in plastic containers. Then it goes to the fridge, and then we have to keep them at this refrigeration temperature for all the supply chain, so all the transportation in the supermarket, and when you go home you also have to put it in the fridge. Other examples of pasteurized products are juice and some alcoholic beverages, mainly beer, and most of the commercial brand beers are pasteurized. Also ice creams and frozen desserts. And pasteurization is very, very important. The other type of thermal treatment is called sterilization, and this is a process where we have higher temperatures and under pressure, and the best examples are canned beans, tuna pouches. So all these types of food that have a high pH and are stored under anaerobic conditions, like a can or a pouch, they can so we have to do these thermal treatments because we don't want Clostridium botulinum to be in these type of foods because it's a very dangerous bacteria. So sterilization is very widely used. So anything that is in a can or a pouch is goes under sterilization category. And we also have another combination which is called UHT plus aseptic packaging, and those are the Tetra Paks, which are the multi-layer packages that we can find. Some of examples of these examples are the plant-based milks like oat or almond that you can find not in the fridge but in the shelf, and you can recognize this type of packages because they have like a plastic lid, and inside you can see, if you open the package, it has like an aluminum foil layer. So I want you guys to watch these videos, and also you are going to have an assignment related with food processing. So these videos will give you the different steps in food processing, and we call these steps a block diagram of food processing block diagram. So the different steps, each step will go inside a block, and we will connect the blocks, and then we will have the whole process. So let's think about Cheetos. Cheetos are snacks, and they will involve a process called extrusion. This is a more advanced process, and then they will be either fried or baked, depending on the type of product. And there's also some mixing with spices and so. Then, for example, the Cheez-Its there's a mixing of the batter, and there's some forming and baking. Then, for example, we have how it's canned soup made, and this is a very good example of sterilization. And it involves a process that is called sterilization or canning, and the cans are filled, sealed, and then they go into a big cooking vessel, and there's high temperature and pressure to reach higher temperatures, and then they are cooled down, and they have very long shelf lives, and more than 2 years, and they are stored at room temperature, so no refrigeration is needed. We have chocolates, also an example, and chocolates is a very interesting process because it's a lot of science but also a lot of like craft, and it requires a lot of mixing and temperature control, moisture control, and molding, and so. And then finally we have an example of how Twinkies are made, and we have a combination of different like assembly lines that come together. Like we have the filling making, and then we have the Twinkies making, and then the filling is injected into the Twinkies, and then there's a coating. So it's more a complex process, and in some of your products maybe you will have these type of processes, and we have a lot more examples, but I think with these processing videos you have a better idea, and you can have like a guide of how to tackle your assignment and look for the manufacturing process of the products that you have selected. So to end this presentation, I want you guys to remember or be able to answer some of these questions. So how does processing start? So what are the raw materials involved? What are the steps? What is the difference between processing and manufacturing? Is an antimicrobial a preservative? What are the signs of spoilage? What are chemical, biological, and physical ways to control microorganisms? Does temperature and time exposure matter when heat treatment is occurring? And why does lactose-free milk taste sweeter? So thank you, and if you have any questions, please reach out, and see you in the next presentation.